Hello everyone, welcome to lecture 21 of AREC 333. Today we will start a new topic, which is linear programming. So we finished the production function analysis which is the first big part of this course. And today I will first have a summary of what we have done so far. So I summary both the technical and the economic aspect of production, and also for cases when there's maybe one input, one output, two inputs, one output, two outputs, one input. So I'll have a summary of those economic and technical aspects of the production. And then after that, I will actually start with the linear programming topic. So today, I'm planning to first introduce to you what is a linear programming, and then how can that be used, especially for this course, and finally, how to set up a simple linear programming using an example. I will go into very detail of the how to set up the problem. So don't worry if you haven't taken course. I think there's AREC 214. And if you haven't taken that course, that's okay. So I will make sure that after you take these several lectures, you will have all the knowledge you needed to use the linear programming method to analyze production decisions. And if you have taken 214, then maybe you can move a little bit faster of the linear programming lectures. Maybe you already have some knowledge on this. And there are new readings here. So I would recommend that you read Deburden chapter 22. And that is more related to, he has a very brief introduction of linear programming or mathematical programming. And then he went to talk about how was that related to the production. He has a very simple example, but I don't think we will get to the how to link linear programming with the production decisions we have started so far. But this chapter of the burden may be good for several lectures of this course. And Rasmussen, again, here it is probably a little bit advanced for you guys. There's a example in chapter 20 that I'm gonna use, and if you feel it difficult, you probably can skip chapter 18 and chapter 19 and go directly to chapter 20. And there's a new reference here, which is Kim et al. 2018. So I already put this on the course website in the reading list. So there's a link to this reference. And I also have on the bottom of this slide provide a link to this book. It's a very short book, I think a little bit longer than 100 pages. And it went into, if you haven't taken 214, AREC 214, then probably it's good to go through chapter 2 and chapter 4 of this reference. And there's also another reference that you can use to get yourself familiarized with linear programming, and that is Paris 2016. So that one is more towards linear programming for economics, and so there might be some part of it is not relevant for production economics, but it should help you understand what the basic linear programming is. Okay, let's have a summary of what we have covered so far in this course. So we have covered actually mostly the technical aspect of production and the economic aspect of the production. And then for each of those, we talked about one input, one output, two inputs, one output, and then two outputs and single input.
So first, I wouldn't go to the details, but this slide is about the technical aspect. So we start very slowly with a single input, single output case, and we did mention in that case, the marginal physical product was a very important concept there. And then we also introduced the we also introduced the 3 stages of production. And when we have 2 inputs and single outputs, very important here is the concepts of isoquant, isocost, and rate of technical substitution. And when we come to the 2 output single input case, this is actually analogous to the 2 input single output cases, because isoquant is analogous to the product transformation curve here. Isocost is analogous to the isorevenue curve there. And rate of technical substitution is analogous to the rate of product transformation. So that's the most important concepts of the technical aspect. And we actually spend a lot of time on the economic aspects. And I here listed under the single input, single output case, then we did profit maximization from both the input and output perspective. And then when we have 2 inputs, we first introduced the idea of cost minimization, and then we also did profit max from the input and output perspective. I will cover the conditions for all those different max and minimizations in a later slide, but here rather to list out what we have done so far. So when there's 2 outputs, single allocable inputs, we did revenue maximization, and we also did profit maximization. So when there's single input, single output, the profit map from the input perspective, the condition is MVP equals to MFC, and from the output perspective, it's MR equals to MC. So those are the optimality conditions when there's only 1 input and 1 output. And if there's perfect completion, the conditions can be simplified, and also I will provide that in a later slide. So when there's 2 inputs, single outputs, and we did both profit max from input and output perspective, and we mentioned that there's a duality relationship between those 2, which is linked by the cost minimization problem in between. So if we want to do a profit max from the output perspective, the variable cost is actually derived from the cost minimization problem. So in fact, so when we're doing profit max from the outputs, it's actually first cost minimization for each level of output, and then after that, we're choosing the optimal output level. And when there's 2 outputs, single input case, we did revenue maximization, and we also did profit maximization. And here, the revenue maximization is analogous to the cost minimization problem that we did for the 2 inputs and single output case. So I put together all of the optimality conditions here in this one slide, and let me actually explain what are those. And I hope this will help you sort out all of those optimality conditions. So first, this is profit maximization condition from input perspective. And these conditions here, as you can see, there's 2 inputs, but if there's only 1 input, 1 output, it also worked. So when you have 2 inputs, the optimality condition, or the general optimality condition, is MVP equals to MFC for each of the inputs. When there's only 1 input, then it's easy. You don't have the subscript anymore, so it just becomes MVP equals to MFC. So under perfect competition in both the input and output markets, then we can write MVP as P times MPP. P here is the output price. So, and then we can write the MFC as the input price. So this is under the perfect competition condition, and our optimality condition becomes like this. And from the output perspective, it is actually also similar to the input case. Is if there's two outputs, then the condition will become the MC and MR for each of the outputs are equal. And if we only have one output, then again, we don't have this subscript anymore. The optimality condition is MC equals to MR. And also, under perfect competition, we can further write those conditions a little bit differently. And we actually have this price equals to marginal cost. So this is actually the marginal revenue under perfect competition. And if we rearrange the terms, we actually get this equal marginal return rule. And not just equal marginal return, but it has to equal to the price of the allocable input. So that's the optimality conditions from the output perspective. And as I mentioned, from the input perspective and the output perspective, when there's two inputs, it's actually there's a duality relationship, and that was linked by this cost minimization problem. And the cost minimization problem, we actually already assumed the output level is given. So for each given output, and remember, each given output is along one isoquant curve. And along that isoquant curve, what is the point that you will find out the least cost? So it's also called the least cost input combination. And the condition for the cost minimization is this condition. And this one actually can be derived from the profit optimization conditions. So here it implies, so profit maximization implies input implies cost minimization. And from the output perspective, and I do want to mention here that this condition, if you translate it into the economics, it actually graphically it means that the slope of the isoquant equals to the slope of the isocost. And I believe you have seen this before, which is this is the isoquant and this is the isocost, and that point will be your cost minimization point. And again, analogous to the input combination, we also have output combination, where we instead of solving a cost minimization problem, we have to solve a revenue maximization problem. And this is when we have two outputs and single allocable input. And again here, the optimality condition can be derived from the profit maximization conditions here. So P1 over P2 is equal to the ratio of the two MPPs, and it's also linked here. So the profit maximization implies revenue maximization, and for a revenue maximization, to be profit maximization, this actually equal to BR1. So this is the actual condition for the revenue maximizing output production level to be also profit maximizing. We also spent some time talked about the input demand functions and output supply functions, and I also put here how you can derive those functions. So first is the input demand functions. As we mentioned, the input demand function, one of the key assumption is that the firm is profit maximizing, and if that's the case, the input demand function actually derived from those conditions. And you have to remember that your x1 and x2 are functions of P, R1, and R2. And when there's only one input, it's part of the MVP curve. And from the output perspective, we can derive the output supply function. And again, we have to use this condition, this optimality condition, to derive the output supply function. And when there's only one output, it's part of the MC curve. And we also mentioned how we can derive the expansion path. So this is when there's two inputs, we can derive the expansion path from this optimality condition. So expansion path will be x2 as a function of x1. And if you plug this expansion path back into the production function, then you can get the conditional input demand function. And from the conditional demand function, input demand function, you can derive the VC. So you actually need this VC to solve the profit maximization problem from the output perspective. And analogous to the two input case, when we have two outputs, we can also derive a expansion path. However, this time we're deriving the output expansion path.
So in AREC 333, there's usually three groups of empirical tools to analyze production decisions. And what we have covered so far, the first big group, which was the production function analysis. And we did some what I will call classical optimization problems there. We did the profit maximization, cost minimization, revenue maximization, output maximization, and so on. So that's that part. And then the second empirical tools is linear programming. And a linear programming can be applied to some production decisions with specific production type, for example, linear production, and maybe also Leontief production. And there will be a third type of empirical tools, which is budgeting. And last year, I covered both enterprise budget and partial budget. I will leave that to the end of this course. So after we're finishing with linear programming, I probably will spend some time on another topic, which is risk and production that is linked to that will be linked to some of the problems that we will study in the linear programming part, and that probably will also have something to do with production function analysis that we have studied. And then at the end, we will go over, we will spend maybe 1 or 2 lectures on budgeting. So first, what is a linear programming problem? And basically, you can tell from the name that it's linear must be an important property. So usually for a linear programming problem, you have to determine the optimal value of a linear function, which defines the objective of the problem. So for example, one example is that y equals to ax1 plus bx2. So this is a production function, and it's a linear production function. So we explained at the beginning of this course what's linear and what's nonlinear. So usually when it's linear, if you draw the relationship of y and your x, then you get a straight line. And when it's nonlinear, for example, if we have y equals to ax squared or maybe cubed, then the graph you get will be nonlinear. So this is an example of a linear production function. It could also be linear revenue function, linear profit function, linear cost function, so on. So the objective is try to find the optimal value of that function. So we actually, in the previous lectures, we already used a different method, which I call them classical optimization method. We have already used a different method to find the optimal value of a function, but it's not necessarily linear. So here, if the objective function is linear, and also there's constraints. So in a linear programming problem, the constraints are also linear. So you might have x1 plus x2 smaller than 10. So what does that mean? Means that maybe x1 and x2 are the length that is used to produce maybe 2 different outputs, and then you have a total of 10 hectares of land available, so you can only use less than that amount of the land. So it's a constraint. In the previous lectures, when we actually saw some problems that we have to optimize a function subject to some constraints. So in those lectures, we introduced there's a method called Lagrangian function, and that we only use the very simple example of maybe like at most one constraint, and then try to solve that problem. Here in the linear programming problem, the function form are simpler, so they are linear. Before we saw nonlinear, both objective function and constraint. So here, the functions are linear. However, we might have more constraints. So it's probably difficult to put this into a better understanding by just talking what is a linear programming problem. I will give you an example. However, it's probably better that you get to know some of the terms that we're going to use for linear programming problems. So there are several key properties of linear programming problem. First, there will be an objective. So the objective usually is maximization of something or minimization of something. So we have already seen the profit maximization, cost minimization. So those kind of problem before. And there will be constraints. Usually the constraints are, for example, you only have this amount of resources or inputs available. Then if that is a constraint limiting your production, then what is the optimal objective function value that you can get? But there could also be constraints about the outputs. For example, if a farmer signed a contract with a buyer, then maybe the farmer will have a constraint of providing a certain amount of output to that buyer if that's what's written in the contract. So in that case, the constraint will be on the output. And again, in linear programming problem, all the equations that you will say will be linear, and you will hear me talk very often the activities or the choice variables or the decision variables. So usually those decision variables is similar to what we have seen before. What is the optimal level of input to apply to use, or what is the optimal level of output to produce? So in the linear programming problems, the decision variables will typically be those two types. So just to give you an example here is that, for example, the objective function, it could be a profit function, then it is the revenue minus the cost of production. And for a constraint, I already explained this one. And the other one is, as I explained, if there's a contract and for some reason the producer has to offer at least 5 units of output. So I think an example is the best to illustrate the idea of linear programming problems. So I have a word problem. So this problem is what we're trying to solve. It's not a math problem, and one of our job is when you saw some problem like this, or if you have a real world linear programming problem that you want to solve, the first step is how to actually set up that problem. And as you will know when we go through the linear programming lectures, that is actually the most important step, is set up the problem. Once you set up the problem, I actually will show you guys how you can actually, once you set up the problem, you can use Excel solver to solve that problem. And then another objective of this course is how do you interpret the results after you solved a linear programming problem. But we will first focus on how to set up the problem. The solving is actually easier, and the purpose, it's not the objective of this course to explain to you what's the different method that you can use to solve the problem. So I will just show you how you can type it in Excel and then get it solved. So we are going to skip the intermediate steps of how was that exactly solved, and I don't think that's the focus of this course. So here I have a example. So maybe you should pause here for maybe 1 minute and read this example. You don't have to read like every detail and remember every number here, but have a general idea of what is the problem here, what is the objective of the farmer, and what are the constraints that the farmer is facing. Then I will actually guide you step by step of when you're given such a description of a problem, how can you set up the problem. So let me actually first show you what is the problem that is already properly set up, the linear programming problem. So you will notice there are several components of this problem, and it's actually what we have explained here. There's objective constraints, there's activities, and you can check that all of the equations are linear here. So let me actually show you what are each of those. So this one is your objective function, and there are 3 constraints. I gave them each a name. You can give them different names if you want, and that's totally personal preference. And at the bottom here are the 2 decision variables. So we have all those elements, and if you check all of the equations here in this example, you will find that they are all linear, and there's a reason for all of them being linear. Is actually much easier to solve, and if they are both nonlinear, or at least one of them is nonlinear, then it's more difficult to solve. It's probably a little bit easier to solve if this objective function is nonlinear. That's probably much easier than if your constraints are nonlinear, then that's more difficult to solve. So I might, after the linear programming lecture, I might introduce to you, if we have a quadratic objective function, then then how can you solve that quadratic programming problem. But we will not cover in this course when the constraints are nonlinear. So I will show you what are the steps. So there are basically 4 steps of setting up the linear programming problem. And then we're going to go through those steps one by one. And at the end, after we go through all those steps, we will end up with this format, this mathematical format of the linear programming problem. And once you're able to write your problem this way, then it is fairly easy to translate this problem into Excel and use Excel solver to solve that problem. So the first step is you have to read the verbal problem well enough so that you have a complete understanding of what it entails. So this time I will ask you to read the problem in more detail. And we are gonna actually go through the step 2, 3, and 4. And then we will find out we will identify all of those elements listed in those 3 steps. So here is the problem, and please read it again. And then the next objective we're gonna do is to identify the activities or the decision variables, and that is embedded in the verbal problem. So let's actually have a more detailed definition of what is an activity so that you have a better idea. So basically, the activities or the decision variables you have already seen in previous lectures is the amount of input to use or the amount of output to produce. So it is, here I have several bullet points here, and I explained to you it could be the inputs or the output quantities, and basically an activity is a blueprint of the technologies. So once you decide what is the activities, then you probably can have a very good idea of what is the production technology. And why do we have to identify the activities first? Is because the objective that I showed you before here. So the objective here, it will be a function of the activities. So in order to write the objective function, you actually have to first figure out what are the decision variables or what are the activities. And when you're trying to identify that here this time, the unit you should also identify, because in the verbal problem, there are different units flying around there, and you have to make sure that when you put them together, it actually makes sense. And I think you have already saw some of the unit problem in your assignment, and but don't get panic about those units, and I will show you how you should be careful about those units in order to set up the problem, the linear programming problem properly. And you actually can set up your problem differently than other people depending on the unit that you choose. So sometimes which unit to use is entirely also a personal preference, and you can get your problem solved either way. So when you're trying to identify activities, you generally try to find in your verbal problem an action verb, something like invest or produce, buy, a lot of other words. Those are generally an indication of the activities. So in our verbal problem, here I indicated here, it is growing potatoes and or tomatoes. So the activities in those in this example is actually, there are 2 activities. One is growing potato and the other is growing tomato. So when you're reading this, after you finish reading this problem, I hope you can identify that this is the decision variables that the producer is trying to control in order to achieve some kind of objective. So there's 2 activities here. What are the units? So go back here, and if you pay attention here, it will say there's a 10 hectare available for growing potatoes and tomatoes. And it actually, there's several other places. For example, there's saying that there's 2 hectares of tomato that need to be produced. And it also mentioned each hectare of potatoes requires some labor, and tomato also requires. And based on those information, then you probably can decide that for your activities, it is the hectares of land that is going to be used to growing potato and growing tomato. That's the unit of the activities or the decision variables there. So there could be different units of chosen. So for example, you could choose the unit of yield using kilogram or ton, and that is a personal choice. Sometimes choosing one over the other makes your life a little bit easier, but probably you can only tell by trying both. And if you're trying one and it's really difficult, then probably you should stop and switch to the other one. So the next step that you should do is once you find out the decision variables or the activities, then you should be able to formulate your objective function. So how do you formulate the objective function in this example? So you can say in this problem, I said this farmer is trying to find a combination that will yield the highest profit. So that is an indication of the highest profit is the objective of the producers. So there are also other possible objectives. In this example is profit, but there could be cost or sales or output level and so on. So how do we actually calculate the profit? There are a lot of information given in the example. How do you translate those information into the actual profit? To calculate profit, you first need to understand what is profit. So we have spent quite some time in this course trying to maximize profit. I hope by this point you know what is profit. So profit is the difference between total revenue and total cost. And of course, this is from the output perspective. So we can also formulate profit from the input perspective, which is the total value of the project of the product minus the total factor cost. So that's the formulation of the profit from the input perspective. So in this example, we're actually going to use the output perspective definition of the profit. It's because there's actually both revenue and cost information given in the verbal problem. So we need to identify which are the total revenues and which are the costs in this example. So if you read the problem again, and you can probably tell that here this sentence is saying that the revenue that the producer can get from producing potato is 4,000 per hectare, and the revenue that the producer can get from producing tomato are 3,000 per hectare. So there's two sources of revenues, and the total revenue will be the revenue that the producer can get from both potato and tomato. So that's revenue, and we also need some information about the cost. So here in this example, there's only one type of cost, which is the fertilizer cost. And so pay attention to those critical word like cost, revenue here, or those concepts. So here it is 1,000 per ton for fertilizer. So the cost of fertilizer is the same for both tomato and potato. However, the rate of applying the fertilizer is different. So for potato, it requires 1 ton per hectare. And for tomato, it requires a half ton per hectare. So you need to use different rate of fertilizer for growing those two different crops. And I have a very detailed calculation of the profit here. So first, for potato, the revenue is 4,000 per hectare. And the cost is, there's only one cost. There might be multiple types of costs later on, but in this example, we want to keep things simple. So there's only one type of cost, which is fertilizer. This is a unit cost of fertilizer, and this is a rate of application. So you want to check that your unit will match, because in the revenue is dollars per hectare. And in the cost, it's actually here is dollars per ton. So if you don't have that information, the unit actually doesn't match. One is dollar per hectare, the other is dollar per ton. So that wouldn't match. However, if you multiply this unit cost by the rate that's applied, this is ton per hectare. Then if you multiply those two, the unit you got will also be dollar per hectare. So in this example, I try to keep things simple. However, it could be different. For example, if I gave you information, it's not 1 ton per hectare, maybe it's 1 ton per square meter, then you actually have to convert the ton per square meter to ton per hectare. And then you can do that. So you need to be very careful about the units. But as we are just getting started, I do provide the ton per hectare so that your life is a little bit easier. So the profits we can get from the potato, and as you can see here, is a unit profit. So it's the profits per hectare here. And for tomato, it's similar, but the numbers are a little bit different. So the revenue is 3,000, and then the cost here, the rate of application is different. So from tomato, we can see that the profit is a little bit lower than potato. So tomato, we only got 2,500 per hectare. And your immediate response might be, oh, let's just use all the land to produce potato. I probably can get the highest profit by using all of my land to produce potato. And you will soon realize that that's not the case. Sometimes it's the case to use all of your input to produce one output, but in this example, it's not. And later on, you will find it's a combination of both of those, growing both of those crops that will lead to the highest profits. Why is that? It's because these two crops have different requirement for input use, and there's limitations or constraints on the input available. So if there's an unlimited amount of resources or inputs available, then yes, we should put all of the land to produce potato. However, it's different. So there's that constraints, and later on we will figure out what are the constraints. But by now, you figure out the decision variables are those two, and you also figured out what's the profit here. So the profit is the unit profit. So this actually I should write it a little bit more accurate, is this much per hectare, and this P is the number of hectares. So once you multiply those two, then you get a absolute dollar value. So this total profit is the unit profit times the hectares of land used to growing used to grow potato, and same for tomato. So that's the objective function. So we get to the last step of setting up the linear programming problem, which is identify the constraints. So in this example, there are actually 3 constraints, and those constraints actually came from after you're reading the verbal problem, and you have to make sure that you used all of the information that was given in the example. So generally, the constraints also, again, are either input or output limitations. So again, maybe you only have limited amount of land, or you sign a contract, you have to produce at least some level of output. So there are some highlighted information here, and one is that the farmer only have 10 hectares available. So this is the land. And the farmer also signed a contract to produce at least 2 hectares of tomatoes. So it is not possible that the producer only produce potato. There have to be at least 2 hectares of tomato. And there's also some constraints about the labor. So the farmer can use 12 hours per week for the cultivation of the 10 hectares. So there's different requirements of labor use for growing these 2 crops. The potato requires 2 hours, and tomatoes again requires 0.5 or a half an hour per week and hectare. So those are actually the 3 constraints there, and you need to translate them into constraints. So from verbal problem to mathematical equations. After read the problems, I actually identified 3 constraints. I gave them each a name. So my names for the 3 constraints are land, contract, and labor. You can give different names as long as it's help you remind what are these 3 constraints. So what are the constraints here? So first, probably the easiest among the 3 is land. So the land, there's 10 hectares of land. So the limitation will be for the hectare of potato and the hectare of tomato, if you sum those 2, it has to be less than 10. The units here are easy. They're both 1. So no more than 10 hectares of land can be used to produce potato and tomatoes. The second constraint here is also easy. It is contract, and there's at least 2 hectares of tomato that need to be produced. So this T, which is the hectares of tomato, has to be greater than 2. I put another thing here, which is 0 times P. So this information I put it here is for later on when you have all the constraints put together. It actually will be helpful if you have the decision variables in both the objective function and every constraint. You will figure this out later on when you're trying to put the stuff in Excel and have it solved by solver. So a third constraint here is labor. So each unit of potato, there's 2 hours, and each unit of tomato, 0.5 hours. So there's a total of 12 hours. So then the constraint here is 2, which is for potato, 2 hours of labor for each hectare of potato, and half an hour of labor for each hectare of tomatoes. And if you sum those 2, there's a total of 12 hours of labor available. So you have to be careful about the signs here. So here is that the labor has to be smaller than 12. And in the previous constraint, this is actually larger, which means the producer or the farmer have to produce at least. So from those verbal words, you can actually tell whether it's a smaller or equal, or larger or equal to. So those are the 3 constraints, and let's actually put everything together. And then we will have actually the linear programming problem that we have seen. And usually you will put the objective function on the top, and you will say this objective function is subject to the constraints. And those are the 3 constraints here. And you will also tell people that what are your decision variables. Usually sometimes it's also nice to put in this max here, as we have done before, of the decision variables. So maybe it will be better to put it here, P and T. So that means you're trying to change the P and T values so as to maximize your profit.